I would like to welcome you to my presentation about solid-state drive caching, testing, and flexible I/O tester, which is a tool for testing storage in general. I'm Kalisz, and you see some of my contact information on the slide. The structure of my talk is distributed in 5 points. I will present an overview of the problem, a suggested way to a solution in general. I'll talk about flexible I/O tester later on. More in theory, and then in some examples as well. Then I'll go over some theory of caching and the implementation in Linux kernel device mapper cache. Last point is the tests and presentation of some of the results I measured, and obviously some kind of outlook and your questions. The problem normally is if you plan for a storage or you have a storage, that you have some kind of idea what the size, what the performance should be like, and maybe you don't exactly get the performance you want, or you plan new storage, you have some specifications, and you really want to fit the price, so you need to save money somewhere maybe, and this is a place where you would start using caching, but it doesn't always work. I'll talk about that later. So you should have an idea first what you really want for performance, what costs, and so on. You should obviously look out for the capacity and development of the capacity, which most people forget. You should ask somebody kindly to provide you a test system. That was also my case. I had somebody borrowed me two servers for 3 months, so I could really test the heck out of it. And after you buy your storage, you should really verify that the performance is still what you planned for, because some manufacturers actually use multiple hard drives in the storage systems, not just from one OEM, but maybe two. Some people use Seagate and Western Digital drives, and they have slightly different performance, but if you have 90 of those drives, that all adds up. So I would like to present you a way to solution how you actually approach the problem of planning a storage and then, sketching all needed things out. You should plan your metrics first and get the relevant data of the current system or the specification you need. Then you should look out for the storage you might actually be able to buy or construct. The interconnect technology, some people use fiber channel, and some people use iSCSI over Ethernet. Some people have their local storage maybe in a laptop or whatever, mobile workstation type of scenarios. Then you should get your data, the specification sheets for those components, do your measurements, use solid methods, know your tools, and that is where FIO comes in. You should test all the changes you probably made, iterate over those points, and after you purchase, you should verify that you are actually getting what you paid for. So there are some metrics, but people mostly forget one metric, and that is your access pattern. We have a file server. It's not a big file server. It has about 1 terabyte of data, but it's mostly documents, so it's quite many documents. And the problem was nobody knows what documents are how frequently used from this storage. And this is very important because that's the essence of to be able to cache anything at all. So maybe you can talk to me afterwards about those metrics if you really plan on implementing this. Caching also provides or enables storage tiering. We have fast and expensive storage technologies, non-volatile DIMMs, RAM modules with batteries or some kind of technology that is very fast, DRAM-like, but actually doesn't lose any data if you cut the power. You have some very fast solid-state drives. Then, of course, we have spinning Rust, Platris hard drives with different kinds of technology. Maybe look out for the shinglet magnetic recording. That is a bit tricky. And we have slow access. So actually hard drives are not that slow. If you have many hard drives, you get very nice performance actually. You have slow access media, and this is mostly tape drives or, you access Amazon. This still goes over the internet connection. You have some interconnects, some local to the computer internal interconnects, or maybe direct attached cables or something that is very fast, has low latency. But you have also interconnects like SCSI over Ethernet, fiber channel, this kind of stuff, and you have also APIs that Amazon, some object storage, you access it over some kind of API, and it has large latency. So we are at the first point in our way to solution. We start observing. How do you observe a system? You use some tools. You just cannot look at the system that is not 70s anymore and say, well, okay, I think this has some kind of good performance or maybe not. So you use top, SAR, TCP dump maybe, but also newer tools in newer kernels like 3.18 or something. There is the Berkeley packet filter, and you can actually get your metrics out of the kernel directly. In Debian, there is the current stable kernel in Debian 4.9, I guess. There came some tools for BPF. So you are now able to really get very good dynamic tracing capabilities out of your average Linux distribution. Of course, if you are using some different systems like FreeBSD, Solaris, Illumos, you could use dtrace, but that's not our focus here. On Windows, you would use Performance Monitor, for example. You should ask questions first and then try to answer them. Don't blame anybody, Don't say, okay, I think it's the network's performance problem. That doesn't really work. That doesn't bring you forward. You only lose time, believe me. You can look up more resources from Brandon Gregg. He's a chief performance architect at Netflix. Everybody knows Netflix, I guess. They provide about 30% of the American traffic at night. So I think they have good people working on performance, So, and they have some serious storage technologies. So you should really look up the resources from Brandon Gregg. Yes. He's also a very nice guy if you go to a conference and talk to him. You should get an overview of the data on your file server, on your local storage. How is your access pattern? Most consumers do mostly reads, almost no writes. But you have some databases, maybe. You have some sensors in the industry and they collect data. That's write only. You almost never read those data. You maybe do a backup, that's it. Okay? So, Brandon Gregg also provided this overview of some of the tools you can use for performance measurement. So you can look it up on his website. It's very helpful. So, okay, we go to the next stage and to our flexible I/O tester. But you should really first do your observation and gather the performance data. Okay, flexible I/O tester. Written by Jens Axboe. He is a kernel developer, and kernel developers, they write the block storage layer, so they want to test it if they have regressions and some stuff like that. So he developed a very general tool, or maybe even a framework, and that's flexible I/O tester. It obviously works on GNU Linux, but it also works on Windows. You can get binaries. Please ask me afterwards, maybe. It works on macOS, BSDs, Illumos, Solaris, all those AIX. If somebody uses that, HPUX, everywhere pretty much. The tests are done using jobs. You specify jobs. You have a job description, and then that gets executed by flexible I/O tester. We'll go over that later on. You can specify those jobs on the command line or in a config file that looks like ini file. Maybe you had done some systemd units. It's similar to that. In the ini config file, you mostly have a global section and then a section for each job. It's very straightforward. You will know it after this presentation. The specification file can contain some arithmetic. You can, for instance, say, okay, I want to do 512 1 meg accesses, and it computes all that, and you don't have to, do your calculations beforehand. So that's very handy. You can provide expressions, units. Obviously, you can say, okay, I want it in megabyte, I want seconds, so on. So this is how a job looks like. You have a global section in the brackets. And then the job specifications, job 1, job 2, and you see the same thing down there on the command line. So that's pretty much it. That's not very difficult. So if you want to, get a hang of the tool, maybe you don't want to put the testing on your hard drive. Maybe you don't want to write over your SSD. So I provided some tips what you can do to speed up the testing and the learning phase. You obviously use RAM for testing. So you do device. You take a piece of RAM and say, okay, this is my block device now. You can do that in pretty much any distribution now with the BRD module. It's very straightforward. You just put this one line there and you get 1 GB memory as a block device. It's mostly mapped in dev RAM 1 or something. Or you can use the TempFS file system that you can mount that file system in some directory. It takes a piece of RAM as well, but it presents that as a file system. So how would you create a block device there? If you want one, you would DD a file there, and this is a sparse file. Be careful with that. Actually, you just jump to the end and say, okay, this is the interval of my RAM that I want to have as in a single file, but you do not actually write any data. That is provided by the count 0 option. And then you would mount this file as a loop device, and then you have a block device again. So it actually works if you, for instance, in production somewhere, it's not very nice, but you know it's a patch. You can use it somewhere. If you have no space left on your device, you have the logical volume and you cannot partition it again. You do a file, large file, and map it as a loopback device and present it somewhere as over iSCSI. There is your block device. It isn't very performant, but it works. You can verify that you have actually done what you planned for with free -h, so you can actually understand it. Or ls. You can use fdisk, all the tools you normally use. Windows and BSDs have also some capabilities how to do a block device, so you would use that. Some other tips. If you do a lot of testing, please use output format ters. It will save you a lot of time. And you can use minimal as well, the option. So you get a CSV-like output. You can even use the option JSON or JSON+. The JSON+ format, it just provides latency buckets, so to say. So you have more information, but you should be fine with using JSON only. You can parse that much better than the normal output of flexible I/O. You can, before the testing, you can drop your caches. You should read into that, so you have repeatable testing. You can use, just to get a hang of the performance beforehand, before you use FIO at all, you can use time and DD to just verify the access patterns. You can use other tools. You should use the sync command after that, so you actually write the data to the device. FIO has an option that says, okay, direct is equal 1, and that says, okay, really make sure that I am writing to the device, that it actually goes there. You should really look into SAR, the command. It helps with much of the testing. You can run SAR while you are doing your testing with FIO, so you get some nice metrics from SAR as well from that time. It's quite helpful. IOstat is from the same set of commands, so you can use that as well. I discovered while preparing this presentation a nice command IOPing. So you can actually get the latency, the round trip time from your storage device. It's very helpful if you are long-term testing something. Maybe you get a spike in the middle of the night when the backup happens. The latency goes up. Something like that, you can detect that after. You should start with really small tests, get really the hang of it and go from there. I recommend like 30 seconds tests maybe, and then, scale that. You should also make sure you can parse or, read all the data. You can understand this data you are gathering. Because it isn't very helpful if you come in the morning after 24 hours of tests, and you have huge log files, like 10 gigabyte log files, and you don't know how to parse that. You will spend months analyzing that data by hand. I really not know what I'm talking about, believe me. You want to use awk or sed for these huge data sets. grep has some helpful options. -b that takes the line before, and the -a takes the line afterwards. What you searched for. Those kind of small handy tips. It's what I would like 3 months beforehand. Don't use LibreOffice Calc for large data sets. It really isn't helpful at all. You can also use the option in FIO, rate minimum. And this is if you want to simulate a tape drive somewhere. You can simulate sequential accesses like you would write to a tape. And with rate minimum, you say, if my performance drops under this throughput or this or the latency goes over some kind of threshold, that's a different flag, then drop the test, stop here, because that's not going to cut it. And you prevent that the tape device, the tape actually goes very fast in the tape device, so you don't want to stop it. You don't want to, do this kind of shoestringing where you put the tape, stop it, put it backwards, stop it, write again, and then maybe stop again. So that will destroy your tape very quickly if you do that a lot. Okay, some examples. So you can, with the read-write flag, you can specify what data you will generate, what access you will generate. The size is obviously how much I/O you are generating, the block size. You can specify the mix of the read-write. So here I do 70% of read I/O and obviously 30% of write I/O. It uses the direct flag, so it actually goes to the device, makes sure this gets written, and uses the I/O engine libIO. And you have to provide a name for the job, or it will not start. That just really disturbed me at first. Okay, here you fill the device with random data using sequential I/O, because that's fast. You do it all 3 times and verify it. So this would be a hard drive burn-in, for instance. How do I do my own examples? I would go to Anantech maybe, or some other website, and because they have some really good tests of storage devices. And I would look how they do their testing, and then try to formulate my job in a similar kind of way to this kind of test, because they really thought about it. And it's not my full-time job to do storage testing, so I should probably look for the expert knowledge. You should observe your workloads first. What is you want to achieve? You should read the man page, which is actually quite good. You can understand it pretty much immediately. Read through everything and you'll know, okay, I want this to happen, so I need to go somewhere in the first third of the man page and I'll have my information later on. I also don't know it at midnight or something. I have to look it up as well. So there are some references for further work or whatever. Okay, to the caching. There are many caches in Linux and in Unix in general. Starting in the 70s, you already have some buffer caches and stuff like that. In Linux, obviously, later on. You have hard drive caches, you have SSD caches, you have controllers in the way that also do some caching. So where comes the other caching? Why am I talking about lvmcache at all? Well, it works differently, so depends on your workload. It's just one of those implementations that are available, but it's one that is widely supported. Red Hat, SUSE, all supported in their systems. If you don't use the typical file systems, you may think about ZFS or ZFS. It also has some second level cache, kind of. It has the S-log you can actually put on a separate device like an SSD, some fast device, and it has the L2ARC, which is similar to a read cache. It's an evict cache, so everything that gets evicted from RAM goes to the second level device. And maybe if you use Windows, you really don't need all this much. You should use your hardware rate controller and say, okay, there are some SSDs, use them for caching. It will save you some headaches. Okay, lvmcache and lvmcache, what's the relation there? Device mapper cache is the in-kernel facility for caching. lvmcache is the front end for that. lvmcache really makes it easy to use. Else you would need to use the dm setup something commands, and you would really spend all your time configuring your cache, not using it. So, okay, lvmcache started in Linux kernel 3.9. That's already 4 years ago. It's vastly improved over time. You want to use a kernel after 4.2, which is, but distributions like RHEL 7.2 actually imported those changes from kernel 4.2. So you are using kernel 4.2 level lvmcache. So SUSE Linux Enterprise Server should have the facility as well. So, and when you are using lvmcache, you are really profiting from any improvement in the block layer in Linux. So you are getting lots of improvements every release. So you maybe want to upgrade your kernel afterwards as well. Look out for the block multi-queue changes that should improve the performance considerably in the future. So how do you set up the cache? It's about 5 steps. I talked about the DM setup. You really don't want to use that, so we'll focus on lvmcache. It has also a readable man page, so do use it. It has helpful sections. You will be much better off than, you know, reading CyberCity or whatever. You create an origin logical volume that is, you know, the slow device. Then a cache data logical volume this should be on your fast device, on your caching device, on the SSD or whatever. And you should do a cache metadata LV, or you basically must do it. You can put those two on the fast device. You can also split them. The metadata logical volume is small. It's about 1,000 times smaller than the capacity of the cache data logical volume. That's just one thing to keep in mind. Then you create a cache pool from those two, from cache data logical volume and cache metadata logical volume. So now you had three logical volumes. You know, the small, the slow, and then you have like metadata and data logical volume, and you put it in one pool logically, and then you link those two, and that's it. In the man page there are the commandos you need to use, so you just go step after step, and that's it. You can remove the cache pool at any time. The data from the pool will be mostly written to the slow logical volume automatically, but you can prevent that if for some reason you don't want, you will lose the data then. But there are more options how you can approach this, so you're very flexible. You can use underneath of those two. You can use the MD rate. You configure with MD-ADM, so normal Linux administration tasks. I would look into DM facilities for rate in newer releases maybe, because I think that could be faster. I didn't measure that. Because you can say, okay, I have these two devices, I want to split the data between the two. It should be faster because you are not doing some copying in memory and stuff like that. So test it. You can change the cache mode while you are running. The default is write through. You probably want to use write back, so think about it. Write through means if you write something, it goes to the slow logical volume. If you use write back, it goes to the cache, and then that's it. You know, the cache takes care of it later on. But you have no guarantee that you are actually having the data on the slow device. Write through would guarantee you that you actually have the data on your RAID array, something. So with write back, you probably want to have some kind of RAID 1, or maybe some data you don't really need. Good backup is always nice. So you can display lots of information using LVS, show, read into that in the man page. We don't have much time for that now. More to the caching theory. You should really know this one. Caching works by locality in space and time. What does it mean? Well, space means obviously if I have a hard disk or an SSD, I can imagine it as a stream of data, and if I access it here, then I'm very likely that it's statistically verified that I will access some data before or after that. And that works also in time. So if I accessed some data, I am very likely that I'll access this data sometime in the future. And the likelihood drops with time, obviously. So you want to keep that in mind. It actually, in reality, it works like that. You have a huge file server, 1 terabyte of data, and you actually use 20 gigabyte of it, and that's it. You access the rest when you do backup, and mostly never else. Maybe if you do an audit or something. So that's one thing to keep in mind. Officially, it's the Pareto principle mostly. In practice, it's even stronger than 80 to 20 ratio. So you use more than 80% of time, less than 20% of data you actually have. Obviously, caching is a latency, throughput, and cost trade-off. It doesn't work very efficiently when you read or write all the data. For instance, if you do some business intelligence analysis, you read the whole database once and do your analysis. That's it. It helps a bit, but it isn't very efficient. So you need huge caches for that, and then it will work okay. If you do access data in random, the cache cannot work with that much. So yeah. For my testing, I had some serious hardware. I had 2 servers, as I said. I had access to usual SAS drives, some SATA SSDs. I had also some NVMe SSDs, so some quite fast storage. I used CentOS 7.3 for the testing, 64-bit obviously. The hardware specs, you can see the difference between RAID array of hard disks and one SSD. It's quite stark. So that wasn't very lucky what I did, but we'll talk about it. I used 10 concurrent jobs, so this was kind of worst case scenario because I mixed all the workloads that could happen possibly and do it all at once. So the cache had to cope with that in some kind of way, and if you measure the worst case, it can only be better. So that's also some information. I used small caches and small amounts of data, so I could run the tests quickly. I repeated all the tests 3 times. I had 4 ratios in caching, 1 to 20, 1 to 10, 1 to 5, and 1 to 2, and then for comparison, just pure RAID array of hard drives and the NVMe drives. You see left, there are just the hard drives. They have some consistent latency. Those it is the hard drives in the first server and the second server, so it's comparable. That's just for comparison. You see, actually, the caching makes the latency worse at first. Well, that's actually not that good, right? And okay, so we get throughput benefit because of that. So it's this, it's a trade-off. You get one thing, you lose the other, and you configure it so that you win where you mostly need it. The especially interesting part is if you look at hard drive, pure hard drive, 1 gigabyte cache and 2.5 gigabyte cache. So the ratio 1 to 25 and 1 to 10. And there you see, this is a linear scale, okay? So you see on the left graph, down there is no red, right? So it improved considerably. On the right, you see the throughput is now quite nice. Now it's a log scale, so you can actually discern it at all. A difference this big is actually 2 times difference in latency. So you win a lot by that. And the difference on the right, it's 7 times difference on the average. So that's huge. That's a huge performance jump. In the reality, you would probably see a development like that because, as I said, mostly in the average industry, you only use very small fraction of the data all the time, so it actually scales better than in these tests in reality. Also, we have seen some different access patterns using cheap SATA SSD. I mean, everybody can buy that. And NVMe SSDs that costs more than $1,000 a piece. We have, with the caching, we have higher latency standard deviation, so it varies a lot. Maybe one thing to look out for. And, well, as I said, I tested mostly the worst case by that. I would improve those tests now with all the knowledge I gathered in the last half year. Probably you should do some tests with larger caches and larger data sets, maybe like the terabyte, but it takes obviously longer to test it, and you don't exactly have time for that if you are writing your bachelor thesis or something. FIO has some facilities, so you can do a Pareto or the Zipfian distribution of data. So you actually do this kind of exponential access pattern. You use a very small fraction of data very often and don't use the rest much or nearly at all. You can test different queue depths. Maybe if you have a database, then you don't have queue depth 1. You should couple that with some concrete engines. Some engines, synchronous engines, don't enable higher queue depths than 1, obviously. So you should keep that in mind. It's written in the man page, so you read the man page. And you can do better data analysis when you really know how you gather your data, how you parse it, what you are looking for. So ask the questions first. And maybe you should do a test on real data. That's mostly the verification phase. Okay. There are some references for your usage. I will provide the slides after the conference. So, yeah. And I would like to thank you for you being still there. And I would like to answer your questions now, if you have any. Thank you. We have 7 minutes, probably. 6.
Hello. Do you know if I can use the DM cache or LVM cache with clustered LVM to use it as a local cache on the node?
Sorry, I cannot understand you acoustically. Yeah.
Once more, better.
Yes.
Better.
Yeah.
If you do know that DM cache and LVM cache can be used with clustered LVM as a local cache on the node.
Clustered LVM. Yes. It should. Yes. It should be able. I used this setup with the caching with DRBD in a cluster. So I had a failover cluster, and it actually helps with that a lot because you can cache some of the you can cache some of the latency away from accessing the data over iSCSI or whatever. So it actually helps a lot in those scenarios. Also caching in general. If you do frequent backups, for instance, of your database, the caching helps with that too, because you read from the cache and not from the hard drive. And that's the data that changed. So that's your transaction log you want to save or whatever. Some other question? We have time for 2 or 3 questions maybe. Okay, if you have no questions, then please come to me afterwards maybe, or write me an email. And thank you.